Hi, everyone. This session is how Harvard University improves scalable cloud network security, visibility, and automation. So thank you for attending. We're excited to have you here. I'm Leo Zhadnovsky. I'm a principal solutions architect at Amazon Web Services. And then speaking with me is Tom Achan. He's a manager of cloud architecture at Harvard University. And I worked with him for several years now. And so what you can expect from this session is to learn how Harvard designed and deployed the platform, which utilized serverless architecture to orchestrate the solution that they're going to be talking about from within to protect their most sensitive data and afford students, faculty, and staff the flexibility of using cloud computing. So first, I'm going to talk about some AWS-specific methods for connecting to your VPCs. So how do you connect your on-premise networks to your VPCs, right? There's basically 3 ways to do this. You can do it through a bastion host. You can do it through site-to-site VPN connection. And you can do it through using AWS Direct Connect. So let's talk about kind of the trade-offs between these 3 methods. So bastion host. So bastion host is just an instance running in your VPC. It's going to be running in the public subnet, so you can get to it. You can SSH to it. It's going to need an elastic IP address, so you have an IP address that that you can SSH into or remote desktop into. It's going to add an extra hop to whatever you're getting to inside of your VPC. So for example, if I'm SSHing into an instance in a private subnet in my VPC, now I have to go through the bastion host first. So you can automate that or make that quicker with your SSH config file, but it just adds some extra setup. It's a single point of failure, so if your bastion host goes down, that means you can't connect to your VPC until you bring it back up. You can get around that by using the EC2 auto recovery feature. So what that will do is it'll make sure that within the same AZ, if something happens to your instance, it's just going to automatically reboot. It's going to have the same instance ID, the same IP address, and it'll pretty quickly get you up and running. If there's a availability zone issue, then you probably want to do like an auto-scaling group of 1 across 2 AZs and have some kind of script to get your elastic IP back. But it's just something to keep in mind. Benefit of the bastion host is that it's really simple, right? So it's easy to use. You can get one up and running in a few minutes. It doesn't require a lot of setup. Another benefit of it is that now you really have this one instance that you have to monitor, that you can audit, because everyone is logging in through it. So it's a central point that you can secure, that you can focus on, instead of versus if you just had everything in public subnets that you can just directly SSH into. So then you've got your site-to-site VPN. So the way a site-to-site VPN works is on the AWS side, you set up a virtual private gateway. The virtual private gateway is just our VPN concentrator. And so you set that up, you connect it to your VPC. And then on the on-premises side, you have a customer gateway. So a customer gateway is just a network device. It's going to have to support IKE and IPsec v2. And it doesn't have to support BGP, but ideally should. So what happens when you set up a site-to-site VPN is it's going to set up 2 different VPN tunnels. And so if you have BGP, if one of the VPN tunnels fails, it's going to fail over to the other VPN tunnel automatically. If you don't have BGP, you're going to have to manually fail that over. Just going to be some extra work, and it's not going to be an automated failover. One downside of using a site-to-site VPN is that you can run into a bandwidth limit with your VPN device. So on the virtual private gateway side, I've never seen a customer run into a bandwidth limit there, but on the customer gateway side, your VPN device could have like a 500 megabit limit, let's say, for its IPsec connections. So if you run into that bandwidth limit, now you're going to have to get a higher-end VPN device. But a positive of using this is that site-to-site VPNs are encrypted by default. So now you've got an encrypted tunnel into your VPC. So everything is encrypted in transit by default. So that's nice. Then you've got AWS Direct Connect. So Direct Connect is our product that we offer that gives you dedicated fiber connection between AWS and your on-premises location. So Direct Connect is available in different quantities. So you can get it in 1 gigabit increments, in 10 gigabit increments. Actually, you can get it in sub 1 gigabit increments if you want from some of our partners. There's many POPs around the world. The POPs map to our regions. So for example, we have POPs in Equinix in Virginia, which get you into our US East 1 region. We have POPs out in Oregon, which get you into our US West 2 region, so on and so forth. And Direct Connect also gives you public and private VIFs. So VIF is a virtual interface. The public virtual interface gets you to our non-VPC services. So once you set up a public VIF, you get a BGP route table that's going to have routes to S3, to DynamoDB, to other services that don't exist in the VPC. So you only really need like one public VIF per Direct Connect. Then you're also going to have private VIFs. So private VIFs are private connections between a given VPC and your on-premises network. So the way you set that up is you set up the private VIF, you tie it to a VPC. That VPC can be in the same AWS account as your Direct Connect, or it can be in a different AWS account as from Direct Connect. If it's in a different account, the target account just has to approve the connection. Once it's approved, it ties it to that VPC. It's going to have a VLAN tag associated with it, and that VLAN tag is going to come through on your on-premises side, so you can then map that in your network as you need to. So the nice thing about the private VIFs is you can set up a lot of them. You can go cross account. Now this gets you into your VPC without a site-to-site VPN connection and without having a bastion host. One thing to note though is private VIFs are not encrypted by default. So if you want encryption at rest, which you should probably do, you should just handle that on the app level, which I think is good practice anyway. Another benefit of Direct Connect is that it gives you transit over the AWS backbone for US regions. So if you've got a Direct Connect in US East 1 and you're accessing an S3 bucket in US West 2, you're going to go over our private backbone to get there through Direct Connect. One other thing that you should be mindful of when you have Direct Connect is the routing priority. So, to hook up Direct Connect, you modify your VPC route tables, or specifically for private VIFs. So you're going to have, for example, a route for your static site or for your CIDR block for your on-premise network that points back to over the Direct Connect connection. And you have to know, let's say you have a Direct Connect. And let's say you also have a VPN connection going back to the same network with the same CIDR block. So how do we make routing decisions when there's two routes going back to the same IP address space? So the priorities as follows. First is just going to be static routes in the route table. Then it's going to be BGP propagated routes from the Direct Connect connection. Then it's going to be manually added static routes from your VPN connection. And then it's going to be BGP propagated routes from your VPN connection. So if you have a VPN connection and a Direct Connect going back to the same network, it's going to prefer the BGP propagated routes over the Direct Connect. So if your Direct Connect fails, then it's going to fail over to your VPN connection. So it's important to know that. The other thing that's interesting with a public VIF, if one of your public VIFs fails, that's all public IP address space, so it's just going to fail back over to your regular internet connection. So it should be a pretty easy failover. But and Tom's going to talk about this more, but what we see customers do is, you can set up multiple Direct Connects, you can do diverse paths between them to, have high availability there. So let's talk about some network security options in AWS. So first of all, how do you control access, network access in your VPCs? You have several tools that we give you. One of them is security groups. So security groups are stateful firewalls, essentially. They are applied at the instance level. Instances can have one or more security groups applied to them. They control egress and ingress to your instances. And then we've got NACLs, so network ACLs. NACLs are stateless filters. They are applied at the route table, not at the instance level. And then we've got route tables. So route tables are applied to your subnets in your VPC. The route tables determine, is this subnet public? Is it private? Can it route back over my VPN? Can it route over my Direct Connect? Can it talk to S3 through a private endpoint? So it basically determines what the nature of your subnet is. Then we've got the internet gateway. So if you want to make a subnet a public subnet, you set up an internet gateway, you tie it to your VPC, you add the default route, so 0000/0, and you point that to the internet gateway. So what that means is anything in a subnet with an internet gateway with a default route is just going to go NAT out directly to the internet through its public or elastic IP, through the instance's public or elastic IP. Then if you want to have a private subnet that can still egress out to the internet, you set up a NAT gateway. So a NAT gateway is a managed endpoint, essentially. And so then instead of going directly out from its elastic IP address or public IP address, your instances are going to go out through the elastic IP address of the NAT gateway. Then lastly, we have something called a S3 private endpoint. So if you want to get to S3 from a public subnet and you don't want to go through NAT, you can set up an S3 private endpoint, and then you have direct routing to S3 without going out over the internet. A nice feature of the S3 private endpoint is that it allows you to give access to all of S3 or only to specific buckets. So you can apply an access policy to your private endpoint. So for example, if you've got your instances are pulling down RPM packages or some kind of security updates off of a specific S3 bucket, you can whitelist only that bucket. You don't have to open up access to all of S3. So now let's talk about some network visibility tools. So we offer you several tools that allow you to kind of see what's going on in your VPC and also in your AWS account in general. So for the first thing, and I encourage everybody to turn this on, is AWS CloudTrail. So CloudTrail is our service that gives you an audit log of API access against AWS. So really, when you use the console, for example, those are all API calls. So when you change your security group rule, or you launch an instance, or create an S3 bucket, that all gets recorded in CloudTrail. It records what IP address that call came from, what time the call came from, the user agent that made the call, all this useful information. So you should make sure that this is on, because if you ever have to audit what's going on in your AWS account, CloudTrail logs are essential. And you can turn on CloudTrail for one region. You can turn on CloudTrail for all regions. I would just recommend you can one-click turn it on for all regions. And I think another good practice is if you've got multiple AWS accounts for your organization, you should have CloudTrail just all flowing in a centralized bucket in one of the accounts, so your security team can audit all those logs. Then we've also got VPC flow logs. So VPC flow logs give you metadata about the packets going around in your VPC. So you can see basically any traffic, where it's coming from, what port, where it's going, anything that goes into your VPC and whether that connection was allowed or denied. So VPC flow logs, the way they work is you turn them on per VPC. They then go into CloudWatch logs, which is our centralized logging service. And from there, you can export them into S3. You can export them into Elasticsearch. So it allows you to export it into destinations where you can consume them with some kind of tool. We also have S3 bucket logs. So S3 bucket logs are essentially access logs for your S3 buckets. So you should turn those on, because then you'll know, did somebody access my data in S3? We've also got ELB logs. So ELB logs are, again, our web access logs for your ELB. So instead of having to turn on logging on all the web servers behind your ELB, you can just turn them on the ELB, and those get stored in S3 as well. And then lastly, we have AWS config. So AWS config is basically a point-in-time snapshot of your AWS account and certain resources in your AWS account. So you can tell, 15 minutes ago, what instances I had running, what were the instance IDs, what ENIs were attached to those instances, what security groups were attached to those instances. So once you consume your config logs or snapshots, what you can do is you can, for example, in your centralized logging tool where you're sending all these things, say, let me list all of my VPC CIDR blocks across all of my accounts. So it lets you get that kind of visibility. So what I would recommend for customers to do is basically take all these logs and send them to some centralized location. So they can be in S3, right? A lot of them end up in S3, but if you ever have to pull them, if you have to manually pull your CloudTrail logs out of one bucket and your S3 bucket logs out of another one, it might take you a while to pull and analyze and make any sense out of those logs. But if you, for example, send all these logs to something like our Elasticsearch service, or to a partner solution like Splunk, or to CloudWatch logs, basically it allows you to go into that one place and start searching for whatever it is you need to search for. So for example, if you have some anomalous network activity and you're looking for a certain IP address, you can now pull it up and you're going to see where it shows up in your CloudTrail logs and where it shows up in your flow logs and so on. So I think that's something that's super useful for customers. So now let's talk about IDS and IPS, so intrusion detection and intrusion protection systems. And so there's two different kinds of solutions for that, or actually three kinds of solutions for that. So the first kind is agent-based solutions. So these are available in our AWS marketplace. And so the way these work, and some examples are Trend Micro Deep Security and Alert Logic Threat Manager. And so the way these work are, you basically run an agent on your instances. That agent sends data back up to whatever the centralized service that you're running, and you can then go into the dashboard for the service and look at what's going on in your instances. You get alerts if something weird is happening. And so the nice thing about these solutions is they scale. They're non-blocking, so if something goes wrong with the service, it doesn't matter. The agent just stops reporting. I mean, that's not great, but your instances are still going to function. They're still going to have network connectivity. But the costs usually scale by the number of hosts. So if you've got a lot of instances, you could have some cost issues there, right? So the second option is inline solutions. So these are also available on the AWS Marketplace. And so examples of these are Cisco, Brocade, Fortinet, Palo Alto. All essentially have network appliances. You run them, you use them as your NAT gateway, so all your traffic egresses through them. And so once you have those set up, you get inline, it's active protection. But the problem is that it can be a single point of failure, right? So if your device fails, you then have to, your instances can't go out to the internet anymore. So you have to make sure that you set them up in a way that's highly available. So the third option is to egress through Direct Connect. So basically, you have on-premise IDS, IPS devices already. You're going to basically send all your traffic, so your default route is going to go back over your Direct Connect, and now through your own network. So if you do this, right, this also makes your on-premise network a single point of failure. So you have to make sure that your on-premise network is reliable. You have to make sure that your Direct Connect is set up in a highly available way. So what we recommend is, in this case, having redundant Direct Connects. And also, not just having them redundant, you should also have them over diverse paths. So if you have two Direct Connects, but they're going over the same path, and something happens along the path, they're both going to have issues. So you want to make sure that you have diverse paths. Another thing is this makes DNS more interesting because you have split DNS sometimes, and so it's going to make that a little bit more challenging there. And so now Tom's going to talk about Harvard Cloud Shield and how they basically implemented some of these options in practice.
Thanks, Leo. How's everyone doing? It's 10 a.m. Come on. So I'm going to talk about Cloud Shield, and just one thing. We're going to take question and answers after the session out in the hall. I'm going to be available for about an hour. Leo has a little less time, but if you want to talk to us about anything you've heard here, be happy to talk to you after. So Harvard Cloud Shield. What is Cloud Shield? It has a great name. Well, first, it's a network security platform. It's comprised of routers, firewalls, global site load balancing, physical appliances. And it gives us proactive response through IPS, antivirus, and other proactive network security technologies. It's a traffic aggregation and inspection point. All traffic into and out of and between applications in AWS filters through this platform. We use our existing information security technologies for auditing and analysis of traffic, for detection and finding out if anything really bad happened. And finally, it's redundant and geographically diverse. We have 2 points of presence in the United States. Each POP is a mirror image of each other. We have no shared infrastructure or IP addresses, and both of the POPs are separated by at least 400 miles. So I want to talk about the goals and alternatives. Some of these are things that Leo talked about, but for the goals, one of our top goals is provide high availability. We don't want to rely on the Harvard campus network. We want to provide high availability NAT to avoid any issues. And we need to be geographically dispersed, as I mentioned before. We want to provide visibility. So we use tap and span technologies into the network flows, and we take these from both POPs, and we backhaul to campus and use our existing tools. So we didn't have to deploy new tools, new technologies that we weren't familiar with, and we didn't have to split our IDSs to have two different places that we'd have to aggregate later. We wanted to provide next generation firewall protections. So as I said, we want to have proactive response. So intrusion protection, not intrusion detection, because we already have that through our visibility. Inline antivirus, it's not the be-all, end-all, but it's better than some things. It's better than nothing, frankly. We want to provide layer 4 to 7 protections. Most firewalls today, they stop at layer 4. We want to go all the way through the stack where possible. And basic denial of service mitigations. We want to make things simpler for end users. Our on-premise, we have massive amounts of ACLs, very complex, sometimes incredibly hard to get out to the internet. Sometimes they can't get to the internet at all unless they jump through 3 different hoops. So we want to stop that. We want to provide inline web filtering and other protections to limit the amount of post-creation configuration of servers. And we want to remove the need to have multiple systems that do functionally the same thing. We don't need a specific proxy if we can do it all in one box with the capacity we have. So what else did we look at? We looked at security agents, as Leo said. They're really easy to configure, and there's no additional overhead cost. But it is actually more expensive to our end customers. We actually have to make a bigger server that has more memory, more CPU, because these agents consume resources on the server. It makes it very hard to right size for our end users, so ultimately they have to eat some of those costs. And they're reactive. They're on the server. So if something goes off with a security agent, it's already at the server. Something has gone wrong. You want to stop it before it gets to that point. So then we looked at inline virtual firewalls. They replace the NAT instances with virtual firewall appliances, and it gives us that proactive response that we want to have. It allows us to right-size the instances for our clients, so they don't have to worry about that. But it has really high overhead costs. We have to have one instance per availability zone, and you have to make it probably about 3 times the size you would expect to have all the UTM features, as they're all done in software. And the licensing costs on these are very high. The cost per megabit of a virtual appliance, whether it's in Amazon or on-prem, is about 3 to 5 times higher per megabit than if you have a physical appliance. So you really have to factor all that in. We ended up going with a third option as a result of all this. And there's really complex VPC routing. So Leo said you need to be able to self-heal these. You need to be able to route around failures and availability zones. So ultimately, they're really hard to manage, and trying to get the configurations back to where they were just going to be something that we didn't want to do. The other thing we found is, as a result of elastic load balancers, we can't use them to make the inbound more available, because they can only send to the main interface of the instance they're attached to. So we couldn't have multiple interfaces to shard the load where possible. So ultimately, that led us to what we decided to build. And I'm going to go a little bit deep technical, so I'm sure everyone will like that. And I'm going to talk about our network connectivity. This was a very large effort, and this is how we had Direct Connect in 2015. We had no convergence between these two paths, except in Virginia, where we landed in the Equinix facility that Leo talked about. And we had one provider for both circuits. So ultimately, we want to remove the thought of having a single point of failure in Virginia, and we want to have a third provider. So when we were going to deploy our Direct Connect, this was originally what we were going to do this year. So we'd bring in the second provider, we'd remove Virginia, but we realized we had a really bad inflection point in the New York Metro. We didn't have any common spans, we didn't have any common buildings, but they're all right there. And I'm sure, as people know, Hurricane Sandy didn't really do well in that area. So as we built out this solution, we decided to go a little bit crazy, and we put one out to Cleveland. So we brought in a third provider. We have no single inflection points, buildings, or spans. We can lose up to 2 links easily. 3 links, we're hurting a little bit, but we're still functional. And what you see here is the links in blue are site-to-site links, and the links in yellow and red are actually our direct connects. So we have 4 direct connects to AWS. 2 are over the waves that you saw in that picture, and then 2 are physical cross connections from AWS to our routing infrastructure. And then we have the private links, one via Cleveland and one via the 95 corridor. They're all distinct from our direct connect links from provider perspective, and they land in 2 different areas of our Boston metropolitan network. So we don't have a reliance on a single routing infrastructure. We stretch it across our campus backbone. Talking a little bit about our network design. So here we have essentially what we've built at a very high level. We have the 2 points of presence with a route switch platform and 2 direct connects each. Each firewall has 2 direct connects, and it's actually reflected by the route switch. It was really important to us to have 20 gigabit worth of direct connect available at any given time to any firewall. And since we have active passive firewalls, or active standby, they allow it, we reflect them back through VLANs, as you'll see, so we can always have the full capacity of that POP available to either firewall. Each location has 2 global site load balancing platforms, which are not pictured here, and they're doing health checks. So what we found out as we built this is return path from Amazon is not guaranteed. If we send a packet in on the left, it might come out on the right. So what we had to do is we had to make a primary and a standby site. With these global site load balancers, they send a packet in. If they don't get the response, that's essentially the standby site because it went out the other direction. So both sites are actively trying to see if they're up, and whichever one gets the packet back is up. And each location has independent public IP space, internet connections, so we don't have a dependency between either of the sites. The only dependence we have is to get to the Internet 2 research and education networks, we have to cross these point-to-point links. As I2 research and education is not easily accessible from all locations, we bring that back to campus. But if for some reason these IPs get severed, I2 will fall back to the commercial internet. So we're going to deep dive into a single site in really explicit detail. So what you see here is essentially how we've built this system. Each firewall gets a single firewall partition. Think of it like a slice of a cake. The benefit here is it allows us to not buy a whole bunch of very expensive firewalls. We can actually buy a medium large size firewall and load it up to its capacity. Much like virtual machines have allowed physical computing to have a lower TCO, these virtual firewall instances have essentially done the same thing. They're great. You can buy a system and basically use it to its capacity. And all of the traffic has to transit the firewalls into or out of our VPC. That is the only route to the internet, our campus, or other VPCs is through the firewall, except where we have to do back-end connections for real-time database needs. So let's go into this and look at this really in depth. We're going to look at this from a single VPC point of view and how all the routing in the BGP works. So each tenant gets a private autonomous system number, ASN. The router takes in a default route and sends it to the firewall. The router gets it from our upstream internet provider. We don't generate it. We don't want to generate it because if something north of us happens, we want to fail. Each VPC shares a single IP outbound for internet access. That's actually per POP. All of this is per POP. And that's really beneficial for us because we have a lot of providers that really whitelist our IP addresses. So instead of providing them 8 different elastic IPs, we can provide them 2. 2 of our IPs that are owned and delegated to us, so we don't have to worry about them saying, well, that's going to change. Each application inbound gets allocated a 1 to FQDN NAT. What isn't 1 to FQDN? Doesn't make much sense. But really, we're giving it a public and a private IP, 1 each, and we're pointing it at a DNS inside. We're pointing this directly at an ELB, doing the translation. It allows us to deal with scalings or contractions of ELBs or ALBs. And these are realized as /32 BGP announcements up to the router. And these occur on the firewall. Each of the firewalls is BGP peered to AWS, as I said, 1 per direct connect, which are the VLANs and links reflected from the route switch platform. And only we only send default to AWS. We only send the default route. We never send anything from campus. That way, we are guaranteed to have the widest possible network access. And if we need to have more specificity, it's really not a problem. But we use auditing tools, as Leo mentioned, to make sure that if someone puts something into a route table, we've detected that and alerted on that. So this gives us the compliance factor that if someone has a route to the internet and we announce in default route, we win because of the route preference. And the router takes in all of the /32s and summarizes it, sends it to on-campus, the internet, and via the campus, the Internet 2 Research and Education Network. So let's talk a little bit how we did our routing. So what you have here is a sample of our routing system for our direct connects. These are from the firewalls to AWS. What you'll notice is we use BFD and BGP. And we have the lowest timers we can allow for BFD, and we use them on every single peer and hop. It was really important for us to get this. For BGP, what we did is we dropped our advertisement interval to 1 second. That's as low as this one provider provides, and allows us iBGP-like reconvergence times. You can see that we explicitly disable IPv6. IPv6 could create unknown wait times, hold times in BGP. We want to make sure that we know what's going to happen. We don't think we know what's going to happen. And we only allow the AWS CIDR network from the BGP peer. Prevents leaking routes upstream that are completely accidental, but sometimes inevitable. And what you see here, this route map out prepend ASN. This is actually how we do our primary standby site. We prepend our private autonomous system number n times. For the primary site, it's 1 or 2. For the standby site, it's 3 or 4. That way, we always appear further. But we already have the routing relationships created. And if we fail our primary site, our secondary site's the next best route. BGP will naturally reconverge very quickly. And this guarantees us the return path and solves the orphaned packet problem. So this is some of our routing config. You can see we use peer templates. Peer templates allow us to prevent any duplication, having to worry about changing a value in multiple places. So we make sure we have a consistent view and configuration between all of our peers. We have a lot of peers into AWS, so it's important to make sure this works. We use the default originate to pass the default route from upstream down to the router and the firewall. And this will only happen if the router has a default route itself. This allows us to detect and withdraw our routes from AWS. It allows us to fail over sites. We could take out the default route from upstream and everything naturally cascades. And we do this through something called BGP conditional advertisement. Essentially, it's an if statement. If the firewall sees the default route, announce the routes up from the firewall for public IP and the VPC. Else, only announce the infrastructure networks so we can troubleshoot things. And since we're using firewall partitions, one thing we found is the conditional advertisement could theoretically have a problem if a management network leaked into our private networks. So since we have these partitions, our management of the firewall is completely segregated, and we can't theoretically create a unknown split brain scenario where we thought we had everything set, but somehow our campus actually injected the default route. And you can see here we adjusted advertisement interval again. This vendor actually supports 0. So we have 0 upstream, which is instantaneous, but it negotiates to the lowest possible value. So downstream, we actually negotiate to 1 second. And then we aggregate all of the 32s from all of the firewall partitions into a single network and announce them upstream. So for route filtering, these are some of the key items we did. We made sure that we filter the public nets, and we only allow 32s to come from the firewall. We did this on both the router and the firewall to make sure that it's exactly what we want and nothing else. And we also dynamically create this VPC CIDR network from our orchestration system, which I'll talk about. It allows only our VPC network to be accepted from our AWS peers, nothing lower, nothing bigger. So we have a lot of pieces moving here. And what we realized is if we did this manually, it would take us a couple hours, a couple days. It would never be right. And how do we make sure we screw it up or don't screw it up every single time? So we built network orchestration. So we built a serverless architecture for a manager of managers, because we want to avoid managing CPU, disk, memory. We just want it to work. And what we couldn't do was predict how much traffic we're going to use in the future. We couldn't understand if we were going to have 1 API call per session or 4,000 API calls. We would just want to scale. We don't want to think about it. So this gave us the choices of Node.js, Java, or Python. So historically, Harvard has used Python internally. It's a really easy language to learn. So we chose Python because essentially the maintenance is easier for our end users. There's existing knowledge, and frankly, it's just readable. So we had to interface with 5 different network management products. PHP, there's an IPAM system, some firewall management, and global site load balancing. This actually gave us 3 different APIs we had to interface with: REST, JSON RPC, and internal toolset. None of them work the same way. And we used the schemaless database to allow us to pass state between the functions. As you'll see in the next slide, we've split out all of the functions into their own container. And we can update one without breaking the others. So we need to be able to essentially glue them back together. So at a high conceptual level, this is essentially what we built for network orchestration. We made it API first, as you can see here. We didn't want to have to write our own wrappers around this. There were ways to make this work easily. And then we have the serverless functions. They actually interface with cloud and on-premises endpoints, AWS APIs, and on-premises network management virtual machines. And it was critical to us for our functions to be able to source our internal IP addressing. So we don't have to worry about ACLs opening up to some IP we didn't know would always stay the same. So it actually comes back across our private connectivity, and we orchestrate from within the system we actually manage. And we use that schemaless database to provide externalized configuration values, ephemeral session caching to share the state information. And an interesting thing, we have to do the activity logs. What we found was when we made this API first, we lost a lot of context about what was happening underneath the hood without a lot of searching. So we log everything to this database just to be safe, so we have some context and we know it's the values we expect. What did we learn? Oh boy, we learned a lot. From the business perspective, we learned that network security has to be in place first. So what does that mean? We did this probably 2 years into our journey into the cloud, and it's probably the hardest thing to retrofit that I've seen. It's taken us a long time. We're not quite there. So it's really better to do it beforehand. I've talked to several universities about this, and pretty much everyone concurs that if you do it late, you're going to take a long time, and we're still not there. And you need to align with your technology partners and vendors. Some vendors have a very interesting concept of word automation, or they don't really know what you're doing. So be very upfront with them. Make sure they know exactly what you're doing and how you're doing it. Have key business sponsors. So we absolutely had business sponsors inside, but what we didn't always have was the financial sponsors. This is a really expensive project to build. If you don't have a way to pay for it, that's going to be a problem, or charge for it. So make sure to involve the finance people early, but also have technical people that understand what you're doing and can explain it to a broader audience, because constant communication is absolutely essential. What we found is we kept fielding a lot of questions, because this is a really radical change. And when we fielded these questions, we weren't doing it. There was only 2 or 3 of us that were building this system with the orchestration, and it was really hard to constantly deal with interrupts, our day jobs, and build this all at the same time, because we actually still had to do what we had to do on a daily basis. From network design, Stateful failover is impractical. So what we found with our firewall vendors is firewalls are stateful. It makes perfect sense. They need to understand that this packet belongs to this rule. But going across geographic regions didn't always work. And more importantly, when it did, they couldn't support 2 firewalls in a single point of presence. So that was a real problem for us. So we started talking with vendors, and we found that some required the same IP space, the same VLANs, and some just actually couldn't handle the 400 miles worth of latency. None of those were really acceptable options to us. So we worked with one of our vendors, and we found out that they would work with us and create this new way to reestablish session state. Most vendors require a SYN packet for a TCP session. We worked with them to reestablish without a SYN packet. So as a new packet comes in, if we fail over, immediately it reestablishes the session, reevaluates against rule health, and relogs. If you turn on asymmetric routing, which is on some firewall platforms, what you see is it doesn't reevaluate the state, and it doesn't log it. So you essentially have ghost traffic. Failing over sites, it's really important. So we have 2 sites. And we need to fail over about every 2 months or so. So you need to consider this concept called error budgets. If you don't fail over, when you need to do maintenance, essentially the business might be risk adverse, or it'll all crash and burn and someone's gonna come knocking on your door. It's really not what you wanna do. These are supposed to be independent, they're supposed to be copies of each other, so why not fail over between them, since we know we can as fast as possible. So I don't know if anyone's read the Google SRE book, but it's really good, and they actually have this thing called the chubby problem. The chubby problem is essentially a distributed locking system that went down one day. It had never gone down before. And when it went down, everyone thought it would never go down, and it crashed and burned. That's not what we want to do. So these error budgets, we want to fail a certain percentage of the time every single month. And if we don't, then we're not in a good place as technologists to enable our businesses to have this redundancy and have this availability. And then make sure when you do this, it actually allows you to test the DNS revalidation of firewalls, because firewalls have to revalidate their DNSs, applications have to revalidate their DNSs, certain application languages like to cache forever. I'm sure you know which ones. And as the saying goes, if something's broken, did anyone check DNS? Because it's usually DNS. Complying and implementing RFCs, they're not identical between vendors. And you think it'll just work, whatever will just work, it probably won't. And whatever didn't, you think, oh, that'll never work. Well, it will, because you actually thought about it longer. And you'll find that the tiny little minutia will be the things that get you. It's not the really hard problems. So what did we learn about routing? We learned that iBGP and eBGP function differently, not just from their purposes, but their timers and all sorts of interesting little minutia. Turn down that advertisement interval as far as you can. You want to get it as close to immediate as possible, but 1 second, still pretty realistic. And then conditional advertisement is key, but setting it up isn't always intuitive. What we found when we started setting up is we thought it was an if statement. It was actually unless. So it never worked because we had the conditional backwards. And then graceful restart, everyone thinks graceful restart's the best thing because, it allows a soft reset of your peers. You don't have to worry about it. But what we found out is it actually introduces very unique hold timers. We thought we were failing over with 1 second because we'd advertisement interval all the way down, our hold times were down. But with graceful restart on, it actually took 2, 3, 4 minutes to fail over. That's not acceptable in this scenario. So we actually turned it off, pointing towards AWS, and we left it on northbound, but frankly, you don't always need it as long as you've tuned your advertisement interval and some other things as well as possible. So historically, we never used BFD. BFD is by forwarding detection. Essentially, it's a little UDP packet that goes out to an IP, comes back, very much like IPSLA if you're familiar with it. And as long as it gets the response, it's good. But if it misses n number of packets over this amount of time, it will it will notify the BGP routing daemon that that route is no longer valid and anything on that interface is no longer valid. So what it actually allows us, 1 second failover. It notifies ourselves probably faster than OSPF would ever reconverge. And what we found was by doing this, we actually like BFD. We started implementing it all over the place. It's really low overhead, and it's really, really useful. It notifies every single routing daemon. But what we found out is some platforms have undocumented limits. Some platforms say they support 4,000 BFD neighbors, but after 25, for some reason, it says operation not permitted. So make sure you've tested all of this information. And then terminate your public peering at each network POP. So as I said, we have a network POP in New York for Direct Connect, and we have a network POP in Virginia for Direct Connect. In Boston and Virginia. So what's really important is you don't want your S3 traffic or some other public traffic to go all the way back up to campus and all the way back down, because ultimately you've just added about 60 milliseconds to someone that didn't need it. So where possible, make sure you terminate public peering, 1 per Direct Connect, as Leo said earlier. Connectivity. Path selection is hard and critical. What we found is KMZs are really, really important, and get them from all of your fiber vendors. One of our vendors said they wouldn't give it to us. We said we won't buy the service, we'll put it in our service order. All of a sudden we had this KMZ. And you need to overlay these, drill down, 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 down. What you saw from those maps is actually our KMZs overlaid into a map. So that's real, and it's really important. We're doing this all over the place. Because it's not a matter of if things will go down, it's a matter of when. And the only way you prevent that is not by buying the most expensive service in the world. It's by buying the cheaper services and buying a whole bunch of them from different providers. Because just because you want to spend $8,000 on a link doesn't mean it's any better than the one that's $3,000 right next to it. Because these fiber-seeking backhoes, I'm sure everyone knows, they're everywhere. You bury a piece of fiber in the sand and you're on a deserted island, digs up. Hey, you got rescued. And then what happens if DNS is only on the campus, as Leo said? Well, that's a problem, because if all of your links go down, you've now lost DNS. So you want to make sure you think about that. Maybe you put a DNS appliance down with your infrastructure. Maybe you make a copy in the cloud. All of these are possible opportunities, and definitely something you need to think about. And then, as I said earlier, if your Direct Connect only ends in one spot, you're no better off. So you want to make sure you are at least in 2 different Direct Connect endpoints, even for a single region. So orchestration. As you see, APIs are not all equal. APIs don't always exist. And we found that we had to actually reverse engineer a lot. We were in the console of our network products, dumping everything. We were clicking around the interface. And then finally, we figured out this magical potion to make this one call work. It's really not great, but it's where the networking land is at the moment. As you see, SDN, NFV are becoming new things. Netconf, Yang, those are definitely going to help, but they're just not there yet. They're still just not fully implemented across everyone's product lines. So we found that we had to reverse engineer a lot. Sometimes we just gave up implementing something. For our routers, we don't use Netconf, we don't use Yang. We use templates in a templating language that we output to files, and then we upload them. We could easily output it to a server and then use SNMP get. So there's a bunch of ways to do automation. It's just not always intuitive. So network vendors are not software engineers. I'm pretty sure everyone knows this. But what's really important is the documentation is really sometimes problematic. Just like the APIs, it doesn't always exist, and it's not always right. We had one vendor say that nothing changed from this version to this version in this API. Our first call broke. And we went to them and said, you said nothing changed. Oh yeah, we left that in there by mistake. So you know more than your vendor really, really quickly. I think within about 2 weeks, we were telling them some things that they didn't know about their own products. So that's important. But it's an opportunity. And I encourage everyone, if you do this, to seize upon this opportunity. Help them get better. They're not software engineers, so you can actually help them by, we worked with them, they rewrote all of our code. Every single call, they replicated in one of our vendors, and now what we wrote is part of their test suites. It's already caught regressions in their next version. It's really important to take this opportunity and help them get better, because the cloud is that opportunity. And I think a lot of them are starting to see it, they just don't have the internal discipline yet. And then ensure all of your values are externally configurable. So the developer that works for me, and she wrote a lot of this, or all of this, it's about 15,000 lines of code, and it took 3 months. It is a lot of code. I don't know how she did it. But what she told us after a little bit, it was, you guys change your mind too much. Ouch. We changed IP addresses. We're like, oh, that name doesn't make sense. And after about 3 or 4 things, she started, getting a little angry and said, I'm going to make everything externally configurable. Great. And then I just go into the database and I change the value, and magic, it just happens. Because you don't want to redeploy this. We're still in some places that we don't have everything externally configured, so we still are deploying randomly. We're finding problems with how we wrote some things. But by isolating it into different functions and then using an external configurable database, we can solve a lot of the headache, and we don't have to bring in the most experienced people to learn this, because it's modular. It does its thing, and it does it well. And with that, thank you.
Thanks.